Now, before I get into the formal definition of what an automaton does when it's computing, as it's doing its stuff, its thing, what it does, let's review. Let's go back verbally. What's going on? What does an automaton do? Okay, so you have a set of states. You have a set of transition rules, that tell you under what circumstances you switch, you transition from one state to another. Okay, you have a start state, and you have a set of accept states. You accept states. So, and you have an input string. The input string is a sequence of symbols from your alphabet, the allowed symbols in your alphabet. And the automaton, what's it doing? It looks at each symbol one at a time, sequentially, and for each symbol that it looks at, it consults its transition function, its transition table, if you like. So if it's in state I, and the input symbol it's reading at that moment is symbol S, let's say. So it looks for I and S in the transition table and finds that the next state is J. Okay, so it switches to state J. That becomes the new current state. Okay, and it just keeps doing that until it has read the last input symbol, and if the final state is a member of big F, in other words, if the final state is one of the accept states, then the automaton outputs the decision accept. Right? And if the final state is not one of capital F, if it's not one of the accept states, then the automaton will output the decision reject. In other words, not accept. Okay, so that, now you're sort of used to that. We've been doing that a few times. So that's the essence of what's going on. So what we're going to do now is sort of translate what I've just been saying into more formal mathematical terms. Okay, and that translation, that's your from the previous session. That is your formal definition of computation, meaning what an automaton does. Okay, right. So so you have an automaton M, and it's a formal definition. So you use the 5 tuple, the usual 5 things. Capital Q, capital sigma, delta, Q naught, and capital F. Right? The set of states in your automaton, the alphabet, in other words, the allowed symbols in your input string. Delta, that's your transition rules, your transition function that maps, or technically, in mathematical terms, it maps the Cartesian product of Q and sigma to Q. Right? In other words, it looks at its current state, it looks at the input symbol being read at the moment, and from those two maps those two into the next state. So in mathematical terms, it maps, in terms of sets, it maps the set that is the Cartesian product of Q and sigma into the set that is the set of next states, which is Q. Okay, so all right. So now let the input string be of length little n, right? Little n here. So let's say the symbols in the string are w1, w2, ... wn. So these symbols here belong to sigma, right? Yeah, here. So each wi, the ith, whichever, belongs to your alphabet, right? Now, when will this automaton, this machine M, when will it accept this string W, this string? Okay. Well, so from what I was saying before, it reads off. This automaton, it reads off each symbol one by one, and depending on what the input symbol is at that moment, and the current state is. Okay. So let's say we're reading the ith input symbol. So and let's say we're in state Ri. So as we read through, the automaton will be changing its state a lot, right? So it goes through this sequence of states. Let's say we we give an identity to each state, and we'll keep it simple. We'll just use integers. Okay, so we have state 0, 1, 2, 3, ... to n. So we have little n plus 1 states. Okay, so so as the automaton reads through the input stream, its state will be changing, and so it goes through a sequence of these states. So these, so state R0, state R1, ... state Rn. Now these might just be integers, right? So it might be a random, wrong word, a sequence of different integers, and different machines, different automata will have a different sequence of integers, if you like, if you label the states by integers. Okay, so the machine, the automaton, reads through the string symbol by symbol, and it's changing its state. So this is the sequence of states that it goes through until its final state. And if this final state here is a member of capital F, in other words, if this state is an accept state, then the automaton M will output the decision accept. Okay, so well, that's what I've just said here. So if your final state here belongs to the set of accept states, the automaton M will output the decision accept. Right? So that's what point 3 is saying. Now point 1, we're here. So the first state the machine is in, as it starts, before it reads its first input symbol, so that's why you start at R0 if you like, will be the start state, right? Here, start state. So R0, here, your very first in the sequence of states over time. Time is running this way, okay? So R0 will be Q0. So that's just saying that the machine's starting state will be the start state Q0 specified in the 5-tuple, the formal definition of the automaton. Right? Now the hard part is this, harder, relatively. So what's going on here? Now remember, the machine, it's reading off symbol by symbol, and each time the state is getting changed. Now it might change to the same state as the previous one. That's you might have R5 and R6. They might be the same state. That's possible. But anyway, you've got this sequence, right? So now, and that's the sequence. So that means that if the machine goes through that sequence and ends up with a final state that belongs to F, you know that machine, that M, accepts that string, right? So if this is your sequence, if that's what happens as it's going through, then your rules have to make that happen, right? And what I've just said is critical, okay? your rules, your delta, your transition function, your rules that decide what's the next state given the current state and the current input symbol that's being read. So these rules have to give you these states in the correct sequence. So in other words, if you're in state I, the next, and then you read Wi, is that right? Oh, technicality here. I plus 1, then you have to switch. If you in Ri, if that's your current state, then you have to switch to R. So your next state would be Ri plus 1. So it would be the next one in the sequence here. So these transition rules here give you the correct sequence of states as you go through. Okay? So and here's the form where your I ranges from 0 to n minus 1. Okay, so when I is n minus 1, so you get R the n. That's your final state here. So that slight complication here. Why this is I plus 1 here. All right. So effectively, your transition function, your delta, has to give you the correct sequence of states as you go through reading. Right? So these like three conditions. These sequence of states, they obey these three conditions. So that's your formal definition of what computation is. Okay. All right. Now, if the machine accepts this string, then